Hello, my name is Jordan Edmonds and this is my Geography 481 final project titled Impact of the Tubbs Wildfire on Vegetation and Topography. The purpose of this project is to use LiDAR data from before and after the wildfire event in order to evaluate the impact on vegetation and to see if there was a change in the surface topography due to erosion from the event. I originally hoped to see if I could quantify the burn severity of the vegetation, but wasn't able to develop a method to find results. This aspect could potentially be a future project. I'm going to go over a brief overview of the background that led up to me selecting this area and of the Tubbs wildfire for those that didn't get a chance to view my project proposal. I originally wanted to investigate the effect the Caldor wildfire had on the Tahoe Basin of California. This specific event ended in October of 2021. While searching for recent LiDAR data for the area, I found that the USGS is currently conducting data collection activities and the data won't be available until later this year. Because of this, I had to switch gears and look at an older fire that has solid before and after data. I turned my sights to the famous Tubbs wildfire that was part of the Northern California firestorm event in 2017. This massive event saw over a dozen large-scale wildfires burning at the same time across California. The Tubbs fire burned from October 8th through the 31st in Sonoma and Napa counties. To the left is a map showing the extent of the fire occurring about 60 miles north of San Francisco. This event burned over 149 square kilometers of land and destroyed over 5,600 structures. Up until that point, this fire was the most expensive in California history, causing $1.3 billion in damage. Most of the structural damage occurred in Santa Rosa, located at the southern end. The picture at the bottom right shows a completely destroyed neighborhood in Santa Rosa with only a park surviving. Like I said in the previous slide, the Tubbs wildfire burned nearly 150 square kilometers. This is a little large for the project, so I narrowed my study area down to the northernmost section on the southern slope of Mount St. Helena. I chose this area for multiple reasons. First, this area is much less developed than the southern extent of the fire, which means there should be more vegetation. Looking at pre-fire pictures of the area, the mountains were home to lush forests. This area also has the greatest relief found in the Tubbs wildfire extent. I'm hoping by examining an area that has varying elevation will provide evidence of surface and soil erosion due to the fire. This area is also intriguing because the headwaters of the Napa River originate on the southern slope of Mount St. Helena. I wondered if that may impact any of the results. In total, my study area is 3.95 square kilometers, down from an original 7.5 square kilometers due to LiDAR data issues. The image on the top right shows the general area of where my project is focused. For this project, I'm comparing LiDAR data from before the wildfire event and after. The data used before the event was collected in late 2013 and acquired through the USGS's website. I was able to find one large tile to download. The horizontal coordinate system used is NAD83, California State Plain Zone 2. I originally found data from 2019 to 2020 that was acquired from a different source, but began to have issues with displaying it in LP360. So I went back to the USGS website and found a new set of data to download. This LiDAR data was collected over the summer, fall, and winter of 2018 and 2019 with the goal of limiting the presence of water being recorded. This seemed to work because there was no water points in the LiDAR data. The tile size is much smaller than the 2013 data, so I had to download a few to get a good coverage of the area. The horizontal and vertical coordinate systems used also differed, which caused many headaches along the way. Basic workflow that I followed while completing my project, which I'll go through in the following slides. The first step was finding and acquiring the data, which I was mostly able to do during the proposal stage. It wasn't until after that I needed to go back and find better data. The second and most time-consuming is preparing the data. I was able to use several of the LP360 point cloud tools that we learned how to use during the course. Some of these tools were Reproject LES, Height Filter, Draw Shape Feature, Smoothing Point Cloud, and LES Layer Statistics, among others. After the LiDAR data was cleaned up, the next step was to export the layers into raster layers and point shape files in order to use them in ArcGIS Pro. Once added in ArcGIS, analysis of the data began in order to see changes from 2013 and 2018 of the area. Finally, the last step of the project was producing the deliverables, aka this presentation. After I found my data, the next step is preparing the data. The first thing to do was adding the 2013 and 2018 LiDAR data to LP360. Since they had two different coordinate systems, I had to use the Reproject LES point cloud tool to change the 2018 LiDAR data to California State Plain Zone 2. The image on the left is the result of the tool with the two layers in the same projection. Next, I used the Draw Shape Feature point cloud tool to trace an outline of the overlapping areas of the datasets. This would ultimately be my study area, so I can observe changes from 2013 to 2018. Continuing to prepare the data, I needed to find a way to get rid of the extra LiDAR points that can't be used to observe changes. When I initially started this project, I didn't do this step at first and found out the hard way that processing time of various tools took way too long for points I won't even be able to use. After looking at some LP360 user guides, I found the Smoothing Point Cloud tool that essentially clips the point cloud data to a shapefile, which in this case is the study area boundary I made with the Draw Feature point cloud tool in the step before. The next step in preparing the data is looking at the classifications in the LP360 Live View window. Both datasets appear to have been classified already, but I dug into the metadata for each to confirm. Originally, I wanted to see if I could further reduce the amount of unclassified points, so I ran the Height Filter point cloud tool we used in the course. The results of the filter are on the right and seem to really affect the medium and high vegetation point counts. Instead of using the results from the Height Filter tool, I opted to revert back to the original data. The next step for this project is exporting data to be used in ArcGIS to help with data visualization. Using the export wizard in LP360, I exported DEM rasters, DSM rasters, and LiDAR point shape files. Without any analysis, the DEMs and DSMs look pretty much the same. The next and most important part of the project is diving into the data and analyzing it. I first started off looking at the LiDAR count data in the live view, which had some notable observations. The first is the significant decrease in high vegetation points from 2013 to 2018. This could be a possible result of the wildfire event the previous year. There is also a notable increase in ground points, which could have been a result of vegetation being burned. Finally, there are increases in both low vegetation and medium vegetation. Low vegetation could possibly be new growth from the event, while the medium points are from vegetation that were previously covered by high vegetation. Here are two images of LiDAR data in LP360 with a display and classification in tin. One obvious difference is the huge swath of high vegetation shown in the 2013 data and the significant increase in ground points in 2018. There is also a significant increase in low vegetation shown in the 2018 data, possibly indicating new growth after the fire. Remember, the 2018 data was collected in 2018 and 2019, which could have been plenty of time for new vegetation to grow. Here are the raster layers derived from the exported LiDAR points, filtered by first return, ground, and vegetation points into ArcGIS. Again, one can see the major difference of the large area covered in high vegetation in 2013 compared to 2018, and the increase in ground points in 2018. From the exported digital elevation models produced in LP360, I used the ArcGIS raster calculator tool to produce another raster, illustrating the change of the DEM between the two datasets. One can see large swaths of elevation increase, illustrated in shades of brown. The large areas shown are found on the eastern sides of the mountain ridges. Some areas observed over 50 feet of elevation gain on the sides of the ridges, leading down into the valleys. This could be possibly interpreted as an increase in erosion due to vegetation loss as a result of the wildfire. It's also worth noting that even though it's minimal and hard to see, much of the area has a positive increase in elevation. With the exported DEM and DSM raster layers, I developed normalized digital elevation models for 2013 and 2018. I then used the raster calculator tool to show the changes in elevation from 2013 to 2018. The results were a little more inconclusive than the previous digital elevation model change, but you can still see change in elevation in the valleys, possibly caused by erosion of the mountainsides. Finally, to further dive into the data, I developed slope layers from the exported DEM raster layers, hoping to see if there was any significant change in slope from 2013 to 2018. I used the raster calculator tool again to see the change in percentage of slope in the datasets. This information was a little more difficult to interpret, but one can see that there are more negative values in red displayed on the slope change map. This can be interpreted as the topography losing a steepness in these areas, again possibly due to erosion from the wildfire event, but also from natural erosion over the 5 years or so. There were 3 big takeaways observed from 2013 to 2018. Most notably is a significant decrease in the high height vegetation observed from the Tubbs wildfire. This is likely a result of the wildfire, which brings me back to the image on the first slide of the presentation, shown here at the bottom. This is a picture of Mount St. Helena after the Tubbs wildfire. Obviously, there was some effect on the forest. Another observation is the increase in bare ground, again most likely caused by the wildfire event. And finally, the third observation is the erosion that occurred in the study area by analyzing the digital elevation model comparison. The increase in the erosion could have been an impact due to the wildfire. There were several lessons learned while completing this project. The most important is having data in the same coordinate systems. I spent a lot of time reprojecting data in both LP360 and ArcGIS. Same measurement units are also important, otherwise you need to convert meters to feet or the other way around constantly. Towards the end, I started using separate project files for my 2013 and 2018 data. I found that it made the folder structures less confusing and the screen wasn't so cluttered. At least for this project, it was important not to go overboard with a large study area and to keep the datasets small. I initially tried using full datasets and found processing times took forever. LP360 also crashed on several occasions while running some point cloud tools. That's it for my presentation. Thank you for taking the time to watch, and I hope you learned something new about the Tubbs wildfire.